All right. These are problems involving conservation of energy. So let's just start out with the first one. We got Tarzan standing on a 20-meter high cliff, and he swings on a vine to the jungle floor below. I want to know how fast he's swinging when he reaches the jungle floor. All right. The first thing I want to do is just to draw a picture of this. We have Tarzan here. He's got a rope, he's got a vine, and he's going to take it down to the jungle floor below. He's going to swing down there. This thing is 10 meters high. How fast he's going when he reaches the jungle floor. Conservation of energy says that energy never changes. In other words, what that means is that the final energy state, or the initial energy state rather, is going to be equal to the final energy state. And you need to ask yourself where those two occur in each particular problem. So if Tarzan is swinging, you want to know how fast he's swinging when he reaches the floor below. The initial energy state is up here at the top, and the final energy state will be down here at the bottom. So you know when they occur, and you next need to ask yourself what types of energy are present at those two locations. Up here at the top, the initial energy, it's going to be all potential energy. Tarzan is not moving when he jumps off initially. He's not moving, so he's got no kinetic energy to start with. And by the way, when you choose what forms of energy are present, you only have three choices. And I'll write them over here on the side. Your three choices are kinetic, potential, or both. Kinetic energy, potential energy, or both are present. So up here we have U sub G, that's potential energy. That's what that means. It's all potential. At the bottom, notice that it says that Tarzan is swinging and he reaches the jungle floor. That means down here at the bottom, his height is actually, height is H, is actually 0. And if your height is 0, that means you have no more potential energy. So down here at the bottom, all of his energy is going to be kinetic energy. So the initial energy is potential, and the final energy is kinetic. And all we have to do is ask ourselves, what equations do we use to solve for those? Potential energy is mgh, and kinetic energy is going to be 1/2 mv squared. Next, we should be able to plug everything in and solve. The only problem is we don't really have everything we need. We know gravity is 9.8. We know height at the beginning is 20. We know that, or we want to find his velocity, but we don't have his mass. They don't give it to us. And the reason they don't is because you can mathematically get rid of it. It doesn't matter. We can divide by m on both sides, and that makes mass go away. So we don't need it anymore. So mathematically we don't need it. And what it also means practically is that it doesn't matter in the real world. As long as we neglect friction, mass doesn't matter. You can swing a mouse off of that cliff and you can swing an elephant off of that cliff. They're both going to reach the bottom with the same speed because mass doesn't matter. So we can rewrite this equation and it'll be this: GH equals 1/2 V squared. Let's bring this up over here. And substitute everything in. G is 9.8. H is going to be 20 meters equals 1/2 V squared. We're solving for V. 9.8 times 20 is going to be 196, and that equals 1/2 V squared. To get rid of a 1/2, you can do one of two things. You can either divide by 1/2 or you can multiply by 2. And that's what I'm going to choose to do because it's easier to do in the calculator. If you do that, you get 392, and that equals V squared. We don't want V squared, we want V. So the last thing we have to do is take the square root of both sides, and if you do that, you should come out with 19.8 meters per second for V. Let's go on to the second problem. Tarzan is escaping, I hate the word gazelle, don't worry about that. He's escaping let's go gorilla. It seems more jungle-like. He's escaping a gorilla, and he's running on the jungle floor at 10 meters per second. He swings on a vine toward a 10-meter tall cliff. So this one is going to be just the opposite of our problem before. So here's Tarzan. He's running at 10 meters per second. He sees a vine. Aha, I can swing to the top of this cliff. Here's his cliff, 10 meters tall. He's running, he catches the vine. The vine's going to swing up to the top, hopefully. We want to know, will he make it safely to the top? In other words, conservation of energy. Initial energy has to equal the final energy. Here is the initial energy state at the bottom. Here will be the final energy state at the top. We want to know at this point, does he have enough energy to transfer that energy to potential energy to make it up to the top of this 10-meter high cliff? So, here we go again. What type of energy is present at the bottom? Well, down here he is on the forest floor. He's running, so he's got some kinetic energy down here. So on this side, the initial energy is going to be all kinetic. And at the top, if he reaches the top, he will have all potential energy. And actually what we want to know is, will he make it safely to the top? What we really want to know is, how high will he go? What is his height when his velocity is 0? So at the top, we want to know potential energy. Initial energy equals final. In this case, the initial energy is kinetic energy, which we find by using 1/2 mv squared. The final energy is potential energy, mgh. Once again, we don't have his mass, which is a good thing because